All right, the next part of this discussion requires a description of how we explain hybrids between different types of orbitals from atoms to make the molecular shapes that we recognize in our common geometries. This is what we call valence bond theory. Again, this goes back to physics and a discussion of quantum mechanical models that show how electron pairs are shared in a covalent bond. Here's a couple of simple examples. Hydrogen's as simple as it gets, with one electron in its 1s orbital. And when two hydrogens combine to make a molecule, there is an electron pair that is shared between them in that covalent bond. So shared pairs of electrons are covalent bonds still. But how does that happen? It has to happen with 1s electrons from each of the hydrogen atoms. With the second example on this page, we have two fluorine atoms combining, and what we're seeing is that we have 2p electrons in the outer electron shell for fluorine that would have to be combining and shared between the two fluorine atoms, like making a bond, a shared pair of electrons between the two fluorine atoms. So when there's two electrons shared in a single bond between the two atoms, we call this a sigma bond. The sigma bond is the head-on orbital overlap between the two atoms that are sharing the electrons. Another example is with HCl. HCl has the combination of hydrogen with its 1s orbital having an electron that overlaps with one from the chlorine in the 3p orbital, that's its outer shell. And again, the two electrons are shared between the two in what we will call a sigma bond. Valence bond theory then does what? It tells us that there are covalent bonds formed by overlapping atomic orbitals, each of which has to have electrons of opposite spin, and we call that being in the same phase. The overlapping lobes then are going to be with opposite spins, and we call that the same phase to make the covalent bond. Each of the bonded atoms then maintains its own atomic orbitals, that's where they come from, but the electron pair is shared by both atoms, so it's totally shared, and the electrons actually go around both nuclei. Without too much difficulty, I think you can believe that the greater these electron orbitals overlap, the stronger the bond is that results. So in order to do that, we'll make sense of these things by thinking about overlapping orbitals in specific molecules. And one that we would like to do is for ammonia. And we think about where the electrons are in the nitrogen and the hydrogen. If the bonds form from overlap of the three 2p orbitals that are the outer electrons in addition to 2s, but the unpaired electrons are typically what we expect to make bonds, the three 2p orbitals on the nitrogen are going to have to overlap with the 1s orbital from the hydrogen atom. What would you expect the molecular geometry of the ammonia to be as a result? Well, let's think what you would do. So we would have the single electron from each hydrogen overlapping with one of the p electrons, the 2p orbitals, and each of those 2p orbitals occurs at perpendicular to each other in the x, y, and z planes, or axes, as you will. And if that were the case, the three 2p orbitals are exactly 90 degrees apart, but the actual bond angle of the ammonia molecule between hydrogen, nitrogen, and hydrogen is 107 degrees. In other words, it can't be exactly as what we expected from strict overlap of three single p orbitals. This leads into the topic for the next section, which we call hybrid orbitals, which will be in a separate recording.